Well, now,
Yeah.
because I'm an alum at this school and I'm in state, so they have no reason not to give me a position.
We've had three offers accepted so far for the masters next year. If this masters is going to stick around, we need more than that.
How many?
We had 8 the year before.
Oh, what?
And keep in mind, it's a 2-year program, so the 8 are graduating. We need 8 incoming next year in order to keep up the grim look of this upcoming year.
What is tuition for master's students?
It gets waived if you have GSA.
And what is that?
I actually don't know what it is on the top of my head.
There's only 8 students, doesn't have the competition.
Yeah, it's basically, if you're an in-state student, you will have a GSA loan. If you have a GPA over about 3.0 and you're an in-state student, you have a GSA line coming your way.
And
GSA
tuition is
standing.
waived for 2 years and you're paid to do it.
Yes. And you have a position that's about 20 hours a week at about 20 something an hour.
Okay.
I'll talk to you.
And of course, what you're doing for that pay is relevant. You're grading a course that reinforces something that you've seen before, or that you didn't fully understand before, and by grading it and seeing other people's perspectives on it as you grade it, you get a better understanding of that material, so that when you go out and interview, you're able to talk about all of the different approaches that people have, a bigger or better understanding of a lot of the core concepts. So it does really help you.
I know that there's master students that just teach a course. Like I had Justin Salisbury taught me in Cyber 101.
Yeah, you're not forced to do that. You opt into that. And if you do, you're paid. There has to be the demand from the department's perspective for us to have that. But if you're interested in teaching, that's a way to get experience teaching.
I might be interested in that in like 3 years.
Yeah. Yeah. Absolutely.
Oh, no, I stumbled in.
It is something to consider. And then you get to work with a faculty mentor doing some cool research that you're interested in. And that's certainly cool as well. Those who are in game dev saw a presentation from one of my master's students on procedural terrain generation that he's working on right now. I have another student we're in the process of ordering a bunch of eye tracking hardware, so actual glasses and or bars to look at where is your attention, trying to get a better understanding of ADD students in remote environments, ADD students in classroom environments. How can we structure something to better maintain attention in ADD individuals? And we use machine learning to try to figure out and maybe even send notifications. Have your phone buzz. It's not something you have to check, but just when your phone buzzes, it's telling you that you're zoning out. Based on.
Don't let the private companies get hold of that.
Is it possible to figure that out?
It could be possible. Now we have to work on the bioinformatics, because now we need some sort of NFC and a device to track that and bioinformation. Then we will also be working with something like database students.
Right.
With large data, and crunch and map this, reduce the data down, and then process it in some form of algorithm that can sense the standard deviation.
Kiva did some research for us. For the master's program, it's 13,000 a year for grad students, 29,000 a year if you're out of state. And that would be what is waived with a GSA loan. You would not have to pay that. You would have to pay fees, but that's only a couple $100 a quarter. So not too bad given everything else.
They're actually going a chapter.
So let's go ahead and get started. So last time we introduced this idea of trying to model the entire process. What would an NPD8 go through if we were actually going through the LL parsing algorithm from that perspective? So we did that. We looked at the 2 kinds of transitions that we have. We had the kind of within the grammar a production that has non-terminal arrow something where we now replace a non-terminal with something else on the stack. So we have a definition for a non-terminal. Another is if the stack matches the current input symbol that we're looking at, we can shift past that. So we ended up with an NPDA that looked kind of like this. Where on the top, all of these 4 transitions are replacing a non-terminal with a bunch of terminals that are non-terminals. So there's the definition of that non-terminal. The bottom 3 transitions from Q1 are all shifts. They move past a terminal in the input string and pop off a terminal from the stack. So this maps to the concept of an actual grammar parse. So we gave an example of this and showed what it might look like on the stack to be able to do this. So we said ABC is what we are doing. So there is ambiguity built into this table. There is non-determinism built into this table. But if we had an LL1 table that we construct from this, we would be able to remove that ambiguity. That non-determinism would resolve itself. There'd be a correct path to go down. So for the moment, let's look at, so from Q0, the look ahead tells us the next character we're looking for in the string. It's the first character here, this A in the ABCAB. We move into Q1, pushing the S onto the stack. We want to manipulate this S such that the character that is on top of the stack, once we're done with this process, is an A without moving past, without doing any shifts, moving past this A. So we can do that in one step, replacing this S with ASB. Now what's on top of the stack is an A. We can pop this A and shift past this A in the input string, where now the look ahead is a B. With an S on top of the stack, we now want to derive via some sequence of productions. We want the top character to be a B so that we can shift past it in the input string. As we do this, this S can become an A, which can become B capital A. Now we have B on top of the string so that we on top of the stack, so we can shift past this B, pop the B off the stack, shift past it in the string. Now the look ahead is a C. We want to manipulate this top of stack character to be a C via some number of legal transitions. Luckily, A can directly become C, according to that grammar rule from the prior slide. We do that, we can shift past the C, shift past the A, shift past the B, and now we have an empty stack with being at the end of the string. We have that end of string character, that $sign that represents that we're at the end of the string. So now we can move over to Q2 and accept with that bottom of stack symbol. So that's how we're modeling this, and it's mapped directly to what we're doing with the LL. Questions on that as a bit of a recap? Right. Then we talked about building the LL1 parse table. So this is what's going to remove that ambiguity from this process. Because as I guess we can kind of see it here, where this S was replaced with an ASB, and this S was replaced with just an A. How did we know which one of these to do whenever we saw them? We didn't, we had to guess. We had to use non-determinism and fork the process and explore both of them if we're in a deterministic universe. But there was a right choice to make and a wrong choice to make. The right choice here was ASB, the right choice here was A. How did we know that? Or how could we have known that? They become lookups in this LL1 parse table. So we said the rows of this table are non-terminals, columns are terminals and the dollar symbol. And then we are going to fill out the table by determining whether there exists a production that creates the first of the right-hand side being that particular terminal. So we're going to have to refer to our first table that we constructed to be able to do this. Let's get you an actual example of this. We also end up having to refer to follow if first of the right-hand side can go to lambda. So I will actually give you an example, because I think going through this in more detail is pretty useless without the example. So we're going to build an LL1 parse table for this grammar. The first thing we need to do is calculate first and follow. So let's start there. Hopefully remember how to do that. Something like this. Each of these are going to be sets. Let's take a few minutes and fill this out.
C wouldn't be a first or a follow because it replaces the A.
It'd be a first. If,
Because it replaces. the-
yeah, since A could become the C, the first terminal in the derivation of that could be. That wouldn't be in follow. You are right for follow. Anything I've missed? The answer is yes, there's a mistake in here, and I did it on purpose. What have I missed?
You can follow it.
Yes. How do we get that?
That's goes to capital A.
Yes, this S here, S goes to capital A, this A has a B that follows it. So this is complete. Yeah,
It doesn't matter if the dollar signs first or last.
no,
Okay.
they're sets, so both order and multiplicity do not matter.
Just needs to be in the set.
Yeah. Yep. It is perfectly okay to put them last. In fact, I think most of the tables that I will show from the book have them last. So it doesn't matter. So, yes, that is correct. Yeah. Questions on these derivations, how we got there? Maybe a show of thumbs on calculating first and follow at this stage. Awesome, I think we're doing pretty well. That looked good. So now we need to construct, given this first and follow table, we need to build the LL1 parse table. So what this is going to look like now is we're going to have our non-terminals on the left. And we're going to have our terminals on the top. So we're going to have A, B, C, and dollar. Now I'm drawing it last because the book will draw it last for some reason. Doesn't really matter. But we want to fill this table with the right-hand sides of productions, if that production can be generated in the first of that non-terminal. So if the goal is to produce the first character mapping that is an A, and we're currently at an S on the top of the stack, is there a way to get from S to A with a single move? With a single look ahead? And the answer is yes. If we apply this production, then the very first character that's generated from that is A. And we know that is the case because we're going to look for it, because A is in the first of S. So this cell should not be blank. And in fact, it's going to contain ASB. Is there a way to get from S to B? Yes, we go from S to A and A to B. We know that because S to B is in the first table. What we draw in here is just the production to apply from S, which is the A. Same thing with the C. In order to get to the first character being a C, we want this to be an A. Is there a way to get from S to dollar? Is there ever a way for S to get to dollar? There is, but there's only one such way. What is it? We'd have to go to lambda. If S goes to lambda, the first character that it would produce would be the very end of the string. It contains nothing. So since there's no lambda in S, this is going to be the empty set. These are all technically sets because there may be multiple productions that can lead you to a particular character. But we are very interested in tables where there are no multiple element sets. From capital A, is there a way to derive lowercase a? It's not in first of A, so there's no way to get there. What is the production to derive B? It's in first of A. How do we get there? Which production do we use? We get that one, A to B, capital A. So that's what we should write here. To get to C, we just use the production that is lowercase c. Can A go to dollar? No. So for each right-hand side of a production that starts with a terminal, add it to the row, left-hand side column, first symbol of right-hand side. So we get exactly as I've done. I don't know if the way that I asked this makes more sense or the way that this states makes more sense. Feel free to make a judgment call on that. But it gets you the same table. Questions on how we got there?
We could produce the end of string character in a compiler. Would that be like effectively commenting?
Interesting. No, that's just mostly something that gets removed from the program by the optimizer, the code optimizer. If it sees anything that's not part of the program, it's just going to get rid of it. It's not part of the actual compilation process. It doesn't map to any CPU instruction. It's there for the programmer. So it's not part of it, but that's a great question. All right, no questions? Anyone need anything else from either of these tables or derivations of them? All right, let's talk about the algorithm itself for the L1 parsing algorithm. So what we're going to use is a push. If we have a character, push W is going to push the string W onto the stack from the rightmost character to the leftmost character. You can think of top as like a peak. Either one of those is gonna be the same thing. Copy the top symbol of the stack without popping it. Pop removes and returns it. Get returns the next look ahead character in the input string. And that's all we have. So it operates very much like a stack, except that we also have a look ahead. How is termination done? It just gives us accept or reject, depending on whether we end the string with the bottom of stack character on the stack, or if we don't. So we can either terminate with accept or with error. If we accept, the string is in the language generatable by the grammar. Error, string is not in the language. We can see how useful this is if you're using something like the Java grammar to determine whether or not a program is in Java or not. This is exactly what the parsing algorithm can do for us. Do we have perfect syntax, or is there a syntax error somewhere in this program? Once we are ready, we will look at the algorithm itself. So assuming that we have all of these subroutines implemented, the LL1 parsing algorithm is actually quite simple. All we need to know as part of this is how to read from and write to the LL table, which is going to require that we've generated the first and follow table for the associated grammar. So step one would be to analyze the grammar, create a first and follow table. Second, using that first and follow table, we're going to construct the LL table. And then three, we implement this algorithm exactly with this pseudocode that reads from the LL table. So exactly as we've shown, this is exactly the process that we've gone through. Push the start non-terminal onto the stack. We get the look ahead symbol. And then we just loop while the stack is not empty. Look at the top symbol on the stack. If the symbol is a terminal, then we will do the move past that symbol in the input and pop it off the stack. That's only true if it is the look ahead symbol. Otherwise, if it's not what we expect, then it's not in the language. Otherwise, if the symbol is a non-terminal, then we're going to look into the LL table at a particular index. So we look for the symbol and the look ahead, the non-terminal, the look ahead at that cell. If there's something there, then we will apply that production. We'll pop the top of the stack and push from right to left all of the characters in that string in that table, in that cell of the table. Otherwise, if that cell is empty, that means we can't derive the next symbol, the next terminal, from some production in the grammar. And now if the look ahead is not the end of that, then that means we haven't gotten to the end of the string, which is an error. Otherwise, we have the bottom of the stack symbol on the stack. We got all the way through the input, and we parsed everything on the stack, which means that it's in the language. Means we don't have a syntax error.
Just clarify that the get would be the second method.
Get is the look ahead symbol. So it's in the input string. Like the last one we had ABCAB. If we called get immediately, we return that first character, that A. Question?
I don't know if you just said this or not, but in the first, or I guess the else if, what does it mean by if LL symbol if it is not an error, not an error?
Yeah, so we had our LL table before. We had like the A, B, C, dollar, and then some of those were null, this would be an error. This would say there is no production that we can apply to go from the non-terminal A to produce the first character in that being an A. And if the first string, the first character that we're looking for, maybe we have something that looks like this. So the only way to generate an A, there's actually no way to do this through an A, so this would also be an error. But imagine somehow we got to this capital A and needed to be able to produce this lowercase a. Seeing this empty would say that there's no way to produce this within this grammar. So this string is not in this language. On the other hand, if there is a value there, then we apply that rule. We do this look ahead to the symbol look ahead row column. And then we'll pop the non-terminal off the stack and push everything from here. Maybe this is ASB, then we would just push the B and then the S and then the A on the stack. That's all this is saying. And it works. So this is the pseudocode for your last project. I'm not even going to have you come up with all of it from scratch. As long as you know how to make the person follow table, you can use this code as a starting point for implementing LL. That said, there are a couple things that we need to consider before we really get into this.
Even considering how to change symbol and look ahead to actual index numbers to look up in table.
Yes, there's a lot more to go from this, but there are still some extra cases to consider with regards to a grammar. A grammar may or may not be LL1. We'll get to that in a second. But let's get another example. So same grammar as before. Apply LL1 to this string. So what you'll want to do, show the contents of the stack at each step, contents of the look ahead at each step. It's going to mirror, let's go back far enough to where you can see it'll look like that. So you're going to draw a table or a stack table that looks kind of like this. So take notes on whatever you need to about what's embedded within this structure, and then I will go back to the other, and we can try to build a table that looks like this from a parse of that grammar. Do I have everything we need? Right. All right, there we go. So it's the same grammar. It's going to have exactly the same first, follow, and LL table that we've already derived. So now we just need to apply it to this string. Do we think we got there? How we doing?
Keeps going.
So the goal from this is that since we have this table, we no longer have to guess and check which production to apply. This table tells us which production to apply in a potential non-deterministic scenario. So we see an S on top of the stack, and we want to be able to produce this A that is the first A of the string that we're trying to map. So we look at the table at row S, column A, and we get ASB. So what we should do is pop the S, push ASB. We still haven't shifted past the A, so this A should stay the same. Replace the S with ASB. Now we're ready to shift past the A. So we're going to read the A from the string. We're going to pop the A off the stack. And move our look ahead character to be the next look ahead character in the string. Now we want to produce this B from this S. So we look back at our table and see that if we're trying to derive a terminal B from an S, we want to apply the S to A production. So we're going to do that. Pop the S, push the A. Haven't shifted past the B yet. Now we have a capital A on the stack. So we're going to look here at row A, column B, and we see that we want to replace the A with BAC. So we are going to do that. We still haven't shifted past the input symbol. So this is going to, it's not a BAC, that's a BAA. So now that we've done that, notice how there's only ever been one thing for us to apply. There's never been any ambiguity on what we've done so far. We've always known exactly what to do. We can shift past the B. This gets rid of this B. Look ahead's now a C. Now we have a non-terminal on top of the stack, so we can look up in our LL1 table. This A becoming a C should apply the production that is just A arrow C. So we can immediately replace this capital A with a C. Now we can shift past the C. So we'll pop the C, move past this C in the input to a look ahead of an A. Do the same thing, shift past the A. Shift past the B. Since the look ahead is the end of string, the stack is empty. We're done. We can accept. This string can be produced from this grammar. Not only that, we didn't use any non-determinism when we did it. There was always exactly one production to apply. That is what tells us this is an LL1 grammar. The fact that we could do this and apply this in such a way that there was no ambiguity. What would ambiguity look like in this system?
If your row column, like cell had multiple options in.
Yeah, so what happens if we do something like I call BS on this, but aside from that, now we have ambiguity. If we wanted to go from A to B, there would be multiple productions in this cell. When we reach something where we would want to produce a B from an A, now we would have two different potential productions that go here, and we wouldn't know which one to apply.
We need LL2 first.
Potentially. Yes, so we will actually see that this is as simple as this gets, and we can blow up the complexity of this to be able to handle further look-aheads. But there are some grammars that aren't LL for any constant. And that creates a problem where we can't actually use this process. We have to look back at CYK and use that cubic time complexity algorithm. Yes, we don't want to do that. So this is a direct speed up. You can see that from here, we used a linear number of operations based on the number of productions in the grammar and the length of this string to directly map it. Imagine doing this with CYK. How many operations or steps would there have been compared to this with a direct lookup every time? It's a lot less work. A lot less work.
5 cubed, so 125?
That would be the proportion. Yeah, it would be proportional to 125 operations.
So when you're using that table, are you just using that to find what you need next, I guess? Like.
Yeah,
so
whenever there's a
like-
non-terminal on top of the stack, that becomes the row lookup. You use the character that's on top of the stack as the row index, the look ahead as the column index. And that tells you which cell to look at to determine which production to apply. And you'll pop the non-terminal off the symbol, and you will push everything from what is in this table in that cell from right to left. This is going to overlay it, but I'm pretty sure this is exactly what this is. There's no Z for this. I don't really care if you include it or not. It's mostly semantic anyway. But I don't think there are any differences between what is there and what I drew on the board. Not that you can really tell particularly easily. But yes, that is exactly what we did. Questions on this construction using this table? Not including BS in this grammar? Don't add BS to your grammar. It makes it harder.
When we're doing the project, our input file will be like qualified grammar.
Yes, yeah, I will have, just like with your CYK, there will be an input output format. And I will give you exactly what that looks like.
To verify, but get into the correct form.
Yes. Any questions on anything that we've covered so far? I think we have a little bit of time left to explain the concept of LLK rather than LL1.
Are you implementing LL1 or LLK?
LL1. Yeah,
And LOK, you'd be writing an actual compiler at that point.
the parsing step of one, given a particular input type. We're living in a very simplified world here where there aren't too many complicated constructs to worry about. The form of things aren't terribly complicated. The grammar is not terribly complicated. Let's go ahead and take a look at that. All right. Not all grammars are LL1. I missed a spot. If a grammar is LL2 or LL3 or LL some constant, we'll call that constant K, then we need to look ahead more than one symbol in the input in order to remove that ambiguity of which production to apply. There are some grammars that are not LLK for any K, and we have no choice now except to default back to CYK because we can't get any speed up from this kind of table. The question you might have is, how do we identify a grammar that's not LL1? I actually asked this earlier, and there is one or more conflict in the LL1 table. Conflict being defined as there's more than one entry in a cell in the table. So let's give you an example of a grammar that's not LL1. We start with building the LL1 parse table for this grammar, making it as simple as I possibly can. Let's start with just calculating first and follow. Let's get a little bit of experience with this here at the end of class. What's first of S? There's only one non-terminal, so what's first of S? A. The only thing that can start these strings is an A. Perfect. What about follow of S? What does follow of S contain? B and
Money sign.
dollar, yes. So now we build the LL1 table. This is as simple an LL1 table as I think we could possibly do for this. There's only one row, S, 3 columns, A, B, and dollar. S can only go to A, but there are 2 productions that do it. So this grammar is not LL1, is how you would state this. So we can't decide whether when we see an A as the first character in this string, whether it makes more sense to apply ASB or AB as the first step of this, just from looking ahead 1 character. On the other hand, what happens if you look ahead 2 characters? Imagine that there's only one way to apply this second production, S arrow AB. You look ahead 2 characters and you expect to see AB, if that's the case. If we apply S arrow ASB, now it doesn't really matter which S we apply here. We're going to kind of branch this into a couple of possibilities. We either get A, B, B, or we get A, S, B, B. Regardless, if we see the first 2 characters being AA, we know now to apply this production, instead of the first 2 characters being AB, we apply that production. Does it make sense how looking ahead 2 characters now removes that ambiguity instead of looking ahead 1 character? How would we build an LL2 table for this? What changes if instead of looking at an LL1 table, what would an LL2 table look like?
I think once we reach an ambiguous case, we break off and then we add another one variable that looks ahead. Then we have to confirm from there which production. to use.
Okay, you're pretty darn close. Yeah, so instead of having columns being a single symbol here, they're going to be pairs of symbols. So we will use combinatorics to figure out what pairs of symbols can possibly exist. So you would have S going to, now we have AA, AB, BA, BB, A dollar, B dollar, and just dollar. Once you're at the end of the string, you're at the end of the string. So it's a much larger table now, but there's still only 1 row. Almost all of these are going to be empty in this particular case. The only 2 that aren't empty are AB and AA. AA, we say we want to now apply ASB, and AB, we now want to apply AB. Everything else is blank. We can't produce a string that starts with BA or BB, or A and then ends, B and then ends, or just nothing, the empty string. None of those are possibilities within this grammar. So this would be an LL2 table, and we now note that we've gone from having 2 productions in 1 cell to there being 1 production per cell. Since we could construct an LL2 table, we can show that this grammar is LL2. How are we doing? Any questions on that, or what LL2 looks like, or how to handle ambiguity in an LL1 parse table? The next thing to check might be, is it LL2? I think we're going to end here for the day because I don't want to get into the next slide. It's going to take longer than 30 seconds to cover. But if you have any questions about this, I'd be happy to answer them.
Wanted to prove it. It's not LLL.
We're actually gonna go into that next. The next example would either be something that's LL higher than that, or LL that is, there's no LLK, there's no K.
Inductively.
Yeah, we're actually gonna talk about how to recognize it. That is a great point, and I urge you to think about that potentially between today and tomorrow. Do you need induction in order to show that?
Is this sort of how C does its golden rule of left, right as well, where it looks ahead multiple characters and then parse exactly what it is, something like, oh, this is a pointer, but then, oh, this is pointing to a function. So this
Right.
is
I
pointing to a
actually
function.
don't know off the top of my head, but it wouldn't surprise me.
C's file, it's so weird because I know C like 80 whatever was a
Yeah.
one pass compile. Like
Yeah.
before C99, C was one pass.
Yes. I'll bet the book that's out by the elevator on the third floor
I
is telling
actually
you.
adopt that product.
Excellent. I didn't check if it was still there, but it's good to know it found a good home.
As well as the OpenGL library.
On office hours, I probably only have until about 2:15 today, but it's better than Monday or Wednesday, so I can assist you there if you have any questions.
Perfect.